In this problem, we're going to ask how, in the case of real eigenvalues and eigenvectors, how do the initial conditions, and that's going to be our focus, how do initial conditions play a role or bring out certain features of the solution? Let's try that first with the initial conditions listed here. x1 at time 0 is 2, and x2 at time 0 equals 7. Well, that pairing gives us a vector of 2, 7, and that is equal to, here's our solution, we're going to sub in t equals 0. Notice there's two exponentials. When you plug in t equals 0 to those, they simply become 1s. So we're going to have c1 times e to the 0 negative 1, 1, plus c2 e to the 0, 1, 2. So that's how we can solve for c1, c2. As we mentioned, the e to the 1s are simply 1s, so they disappear. And we could do some complicated work to figure out what c1 and c2 are. It's a linear system, but if we take a quick inspired guess at this, we can get there maybe a bit quicker. If we choose c2 equals 3, that'll give us 6, and that'll mean c1 would have to be 1. That'll give us 7. And if we do that, we'll have 3, minus 1, and 2. So yeah, I'll do a quick check here. 1 times minus 1, 1, plus 3 times 1, 2 is negative 1 plus 3 is 2, and 1 plus 6 is 7. So that would be the solution. Now let's look at that graphically. When we did our analysis for the initial conditions, what we just said mathematically is that the initial condition, 2, 7, so we'll go up here to 7 and 2, it can be written as 1 times the first eigenvector, negative 1, 1, plus 3 copies of the 1, 2 vector. And if you go back to when you first learned about vectors in any way, shape, or form, this is the kind of thing you did. We said we've got a point here, and we have a vector. Let's do the 1, 2 vector. It's easier to see. 1, 2 is there, and then it would stop. And then we do another 1, 2, and then we do another 1, 2. So we have 3 copies of that vector. And then we have the 1, negative 1. Draw that in red. What that is 3 of our second eigenvector plus 1 of our first eigenvector. And altogether, that gets us to our initial condition. What that's telling us is every initial condition, because every initial condition is a point on this plane, is made up of a unique combination, unique linear combination of that v1 vector and the v2 vector. Some stretching out of the 1, 2, and some stretching out of the negative 1, 1 vector. Okay, that's making some progress. There is a graphical interpretation to this breakdown of the initial condition into the two components. So that's another term we can use here. The initial conditions have v1 and v2 components. Usually we'd talk about the x1 and the x2 component, but here the natural units, the natural directions apparently, are those dictated by the eigenvectors. So we talk about a v2 component and we talk about a v1 component. So what if we had an initial condition of negative 2, 2, which we see immediately is a multiple of v1, or the vector negative 1, 1. In fact, it's just 2 times that. Well, as soon as we see that, we're going to get c1 equals 2, and c2 has to be 0. There's only one unique way to write this vector as a combination of these two other vectors, and if it's a multiple, it's going to be just a scalar of the one vector here, and the 0 component of the other. And that means the solution that we get is simply going to be 2 e to the minus 5t times negative 1, 1. Well, that's a simple solution. It does not involve a combination of both exponentials. It's just one of the base solutions, and sometimes you might hear it called an eigensolution. It's one of the characteristic solutions, or you might hear it called a basis solution. all of the solutions are made up of these, and this is just one of the two elements that we could pick, and it's not reflecting the other one at all. More pragmatically, what would happen to this particular solution if we let t go to infinity? Well, the only function in here is e to the negative 5t, and we know that heads to 0. So x of t is going to head to, as a vector form, 0, 0. These constants aren't going to have any effect. So if we start with a multiple of this value here, we're going to get a solution that heads towards the origin when we look at the pictures. Well, what if we repeated that? Again, remember we're talking about the vector 1, negative 1. So down at 45 degrees here on this line, if we pick the coordinates negative 4 and 4, or we pick the coordinates 10 and 10, say down here, 10, negative 10 rather, or the value we had in the last example, which is negative 2, 2, all of those are the starting values, and they all are multiples of this first eigenvector, the first eigenvector from the last page. This solution would look like x of t equals 4 e to the minus 5t times that vector. And this solution would look like minus 10 e to the minus 5t negative 1, 1. That same eigenvector. Now, what we're going to do is sketch these solutions now over time. So we're going to imagine these are t equals 0 points. These dots here are the origins, the initial moments. And then as time goes on, well, let's take this example here. We're at negative 4, 4. And then this function here is approaching 0. It's getting smaller and smaller and smaller as time gets bigger, as t increases. And likewise for this one, this is also approaching 0 too. So what do those solutions do? Well, they would start here, and then they would gradually move inwards over time. So this is a graph over time, sketching out points. We would see them moving in towards the origin. And just the same way, if we tracked over time, all the points that start on this line over here, specifically 10, negative 10, those would head in towards the origin. It would be an exponential decay, so they'd never quite reach it. So you can imagine it'd be swoop and then slow and then drag and slow and taper down, almost reaching the origin. But they would always stay on this line because we always have that vector. The only vector in this whole thing is always negative 1, 1. So it'll always be some multiple of that, and that puts you on that red line, guaranteed. So what we're seeing here is by choosing initial conditions that are multiples of the eigenvector, we get a very simple solution that we can actually interpret. Notice the same thing is true if we pick the other eigenvector. So we notice that this initial condition is a multiple of the second eigenvector. And so our solution would look like, in this case here, 2 e to the t 1, 2. This is twice as big as that. If we solve for c2, we'll get the value 2. And in this case, as t goes to infinity, e to the t is going to go to a positive infinity as well. Okay, but you'll notice that once again, we have a simple solution because the initial conditions were a multiple of one of the eigenvectors. And that's crucial. Along that same vein, if we pick other values that are also multiples of that eigenvector, if we think of the eigenvector 2, which is 1, 2, all the points that are multiples of that are going to lie on this line here, and possibly down here as well, including the point 4, 8, that would be up here, the point negative 2, negative 4 down here. And what is going to happen to those points over time? Well, again, the solution is going to have the same form. This one is going to be 4 e to the t times 1, 2. That'll start at 4, 8. And this solution would be negative 2 e to the t times 1, 2. Now in those cases, if we take those points, what's going to happen as t gets larger and larger? This is going to get larger as t goes to infinity, as t increases. And so is this, but there might be a negative sign, so we'll see how that plays out. But the direction is always along that vector 1, 2. So if we start at this point here, we are going to stay on that line because our solution is only going to contain the 1, 2 vector and scalar multiples. So in this case, what's going to happen is over time, we're going to move out and out and out in that direction, away from the origin. If we started here, we would do the same thing. We'd move out and out and out, away from the origin. So we get a different behavior, but a very simple straight line behavior out of solutions that start on this eigenvector. With that in mind, what we've done is broken down what happens in two cardinal directions defined by the eigenvectors. And now we might ask, well, what happens to everything else? Well, it's going to be some combination of those two solutions, just like the general solution is literally a combination of some decreasing stretch of this vector and some increasing multiple of this vector. And the only thing that changes is how much of each of those is going to be present based on the initial conditions. How much of this vector do we have to start, and how much of this vector to get our initial condition.